All right, so well, we're continuing on with forces today, and well, today's all about friction, the force of friction, and there is two types of friction. We have the first one here, static friction, which is the force that tends to prevent a stationary object from starting to move. All right, now that's when something's not moving, you have static friction, but then kinetic, again, those words are in terms of motion, is the force that acts against an object's motion in a direct opposite to the direction of motion. All right, so kinetic friction and static friction. Static friction is the force that we experience when the thing's not moving. Kinetic friction is the force of friction when the thing is moving. Now, static friction, if we're comparing it to kinetic friction, is always greater than kinetic friction. All right, so, and I think a lot of us know that. I mean, if you ever try to push something or move something, it's harder to get it moving than it is to actually move it. God forbid you ever have a car that conks out on you and you have to push it. You realize that pushing the car is a lot easier, or is a lot harder than getting the car rolling. You know, once you get it rolling, it's easier when it's moving, but getting it moving is tough. Now, pairs of materials encounter different results with respect to friction. Again, I think another thing that's intuitive, but you got to write it down. And we're going to look at this a little bit closer. What this really means is, for instance, the friction between rubber and pavement is different than the friction between, say, ice and steel, right? And so I know that's for a kid. As a kid, when I was playing road hockey, when you fall down, or rubber and pavement, say if you fall down, that hurts because you've got scratch because there's a lot of friction between you and pavement. But yet, if you're playing ice hockey on the rink or on an outdoor rink and you fall down, it doesn't hurt because you slide. Well, it does hurt, the impact, but the sliding part doesn't hurt, where sliding on pavement definitely does hurt. Now, because there is two types of friction, there's what we call two coefficients of friction. All right, so our first coefficient of friction, and it's a weird letter here. It's like a U with a little tail on it, and it's called mu. It's a Greek letter, and mu s is what we call the coefficient of static friction. So again, that's when the object's not moving. Then the second coefficient, well, is the same idea again, where we have mu k, which is the coefficient of kinetic friction. We're going to look at these coefficients. Now, what a coefficient, well, we'll get to this, the coefficient part, but a coefficient is a rating of how much friction there is. The bigger the rating, the more friction there is. And there is no units because it's a rating. It's like saying, how big is it out of 1 to 10? Well, coefficients are usually, I think, from 0 to where you have no friction up until, I don't know, around 2, somewhere in there. Now, there's two formulas, and they're pretty much the same because, again, we have two types of friction. And so our first formula is Fs, which is the force of static friction, is equal to mu s times Fn, our normal force. So again, Fs is the force of static friction. And of course, like I said, I just basically going to write down the exact same formula, just change the letters, where Fk, the force of kinetic friction, is equal to mu k, and again, times our normal force. So again, Fk, this is the force of kinetic friction. All right, so let's try to figure, we're going to use our two formulas here and figure out some values. All right, so we get to our first example. A hockey player has an 80 kilogram mass, is standing still, that's key, on the ice and is suddenly pushed by another player. Determine the force of static friction that must be exceeded, I guess, nice little English problem there, in order for the player standing to still move. All right, so here's what we got going on. We have our player, and just to get them to move, you always, because it's at rest, you always have this force of static friction. Now, until you exceed that force of static friction, you are not going to move. But the second that you apply a force and get that object to move, you've overcome the force of static friction. So that's what we're looking at. Determine the force of static friction. Now, again, because they're going to be equal, after they're equal, or after f of a, that's an a there, by the way, sorry about that. After f of a exceeds f of s, then you're into kinetic friction. Now, again, the force of static friction is equal to mu k times our Fn. Now, in this case, again, this object is, or person, I won't call them an object, is 80 kilograms. Now, they are pushing down on the ice with a force of gravity. The ice is pushing up on that person with an equal force, and that force is our normal force. And those two forces are equal because vertically, our net force is 0 because this player is not flying up into the air and they're not going into the ice. So because our F net is equal to 0, Fn is equal to Fg. And of course, our force of gravity is equal to, whoops, I'll get rid of that. Mass times acceleration. So m times g, which in this case would be 80 times 9.8, which, let me see here. I get my calculator and I find that to be 784 newtons. All right, so that's my Fn. I still need my mu k. So what I have to do is use this table, and this table I put on Google Classroom, and I have it here, and so I'm going to have a look at it here. There we go. And so what here is the approximate coefficients of kinetic and static friction. So here's the materials, the pair of materials, right? Because you have to have one pair interacting with another. And so you see the different ones. So here's for mu s, static coefficients of static frictions, mu k, coefficients of kinetic friction. And so in the case of a hockey player, we're looking for steel on ice. And I go down here, and it looks like steel on ice. The coefficient of static friction is 0.1. And again, you can see all the different objects here. All right, so I know it's 0.1, so I'm going to go back. I know that, again, I'm going to write this in here. I just looked at the table. Mu k is equal to 0.1. All right, and so if I now am looking at my force of static friction that's there, I have my mu k, which is 0.1. My Fn, my normal force here, I found out was 784. And so when I multiply those two numbers, my force of static friction is 78.4 newtons. Any more than that, now we start to have kinetic friction because the object will now start to move. The hockey player will start to move after 78.4. So 78.4, 0, 0, 0, 0, 0, 0, 0, and then a 1, our object will start to move. Our person will start to move, I should say. All right, let's try, let's have a look here. Next up, example 2. A horizontal force of 70 newtons keeps a desk 30 kilograms moving at a constant velocity. What is the coefficient of kinetic friction? Okay, so again, I'm going to draw a free body diagram here, a forces diagram. So here's my desk. All right, and again, it is 30 kilograms. We have a horizontal force that is moving the desk at a constant velocity. All right, so here is our applied force. which is 70 newtons. All right, now it is moving at a constant velocity. So this again is Newton's first law, which that means then is that F net, or net force here, is equal to 0, which means if I have an applied force of 70 newtons going to the right, for example, then there is an opposing force that balances it out, which would be the force of kinetic friction because it's moving. That would have to be equal in magnitude, opposite in direction. So it's 70 newtons. So again, horizontally and vertically, actually, our net force is 0, and so our kinetic friction has to equal our applied force. Now, we want to find the coefficient of kinetic friction. So we're looking for our, mu k. Now, again, to find that, we have our formula, and this time we're dealing with kinetic friction. So Fk is equal to mu k times Fn. All right, now again, we are looking for our mu k, put a little question mark there. We have the force of kinetic friction. All we need is our Fn, our normal force. But again, in this situation, this desk is not flying up into the sky and it's not going into the ground, which means vertically, our net force is also equal to 0, which is telling us that, again, Fn is equal to Fg. Now, we're going to change that up a little bit here in part B. But again, so if I find Fn, it's equal to Fg, because vertically, our net force is equal to 0, which, of course, means it's equal to mg, mass times the acceleration due to gravity on Earth. And again, so we have a 30-kilogram desk. That's pretty heavy, actually, but 65 pounds. And our G value, well, we're on Earth, so it's 9.8. Once again, I multiply those two, and let's see here. Oh, nice round number again, 294 newtons. All right, so now I can plug in my values. All right, so my Fk is 70 newtons, equals to, I guess I'll put a little UK in there, times Fn, which I just found out to be 294 newtons. All right, so the last thing I'm going to do here is divide by my numerical coefficient, which is 294. So we got to divide both sides by 294. And I end up, mu k is going to be 70 divided by 2.94. It's going to be 0 point something. And let's see here, I get my calculator going, and it's 0.24. And there's my coefficient of kinetic friction. All right, now, and if I looked at my textbook here, what does that kind of look like? 0.24, kind of like wood on dry snow, sort of. Maybe a little bit rougher than that if I'm looking at my coefficients here. Or rubber on asphalt when it's wet, on the really wet, I guess, because that would be 0.24. So somewhere in there, just a kind of a base ranking. All right, now I'll get to an interesting example here. Part B here. So we still got the same thing going on here. You got a friend helping out who helps moving the desk by exerting a force of 100 newtons up. That's it. Person's just pushing up on the desk. What horizontal force would be needed to keep the desk moving at a constant velocity? All right, so here's our situation. We have our desk, all right, 30 kilograms. Now again, the force of gravity that's not going to change. Our Fk here, or Fg, sorry, our force of gravity is still 294 newtons. Now this desk is still in contact with the floor, and we know the mu k here is 0.24. All right, so that's the same. Now here's what we're trying to find out. We want to keep the desk moving at a constant velocity by applying a horizontal force. So we still have an Fa. All right, we still have this applied force. We don't know what it is. But here's what I am going to say is that now that the box is moving, or sorry, the desk is moving at a constant velocity, we're going to have the force of kinetic friction acting on it. But because it's at a constant velocity, F net, again, this is Newton's first law here, is equal to 0, which horizontally means, so I'll throw that in there. So horizontally, that means F of A is equal to our force of kinetic friction. All right, so if we find the force of kinetic friction, we know what our applied force is. Now, again, vertically, all right, two ways to look at this, horizontally and vertically. Again, as I mentioned, we have the force of gravity pushing down on this desk. The floor will push back up on the desk. We still have our normal force. But listen, we have our friend who shows up here, our buddy. So I guess I'll call that F of B here, our buddy here, and our second applied force, helping out with 100 newtons. Now, here's the key, is that vertically, this desk, again, is not flying up into the sky. It's not going to the ground. So F of net, once again, is equal to 0. All right, which means when I add up my forces here, we're going to have 0 is equal to my Fn, my normal force. Whoops. And I'll put Fn. Oh, man. Let's see if I can get rid of that. There we go. All right. So again, my F net is equal to 0. Now, if I add up all my forces vertically, here's what we've got. We have my normal force plus force from my buddy. I guess we'll call him, or him or her. All right. And then we have the force of gravity. Now, force of gravity is in the opposite way, so we're going to throw a minus sign in here. I'll put that, you know what, I'll put FG in here. All right. So let's start looking at it now. So we have 0 is equal to my normal force. I don't know. My buddy here is helping out with 100 newtons, but I also have the force of gravity working the opposite direction. All right, so I'm going to do a little math here. I'm going to move that minus 294 over to the other side. So change its side, change its sign. I'm going to move the 100 over to the other side. So it's going to come in a minus 100. And that is going to equal my normal force. And if I do 294 minus 100, well, I get 194 newtons. All right. Now, why would I do that? Well, because now I can find my force of friction. Because, again, force of kinetic friction, which, again, is equal to my applied force. That's what we're trying to figure out here. Is equal to my Fn, or my mu k times Fn. All right, my mu k, which we found in example A, is 0.24 times my normal force, which is 194 newtons. And so now the applied force that I have to push this desk with, again, to move it at a constant velocity, is 0.24 times 194, which ends up being 46.56 newtons. And so all this friend did was push up. But yet, look at the force, 46.56 newtons. When I didn't have my friend helping out, I had to apply 70 newtons. So that is, again, a real-life example when you're pushing something that it helps if somebody just simply pushes the object up, because what's happening is you are reducing the force of friction because you are helping out the normal force. You're not allowing, you're helping out the floor, who generally supplies all the normal force. Like in our first example here, the floor applies all the upward force, and hence the friction's greater. But when your buddy helps out, you reduce the normal force, which in turn reduces your force of friction. And so now it's easier to push the same object on the same floor, which again, hopefully is something some of you have had experience with, or just wondered why that is the case. Well, that is what's happening. All right. All right, and so what we're going to look at